Hello everyone. Today we are going to talk about crystallographic directions, families of directions, and the concept of linear density. As you see in this figure, you see the BCC structure, body center cubic, and you see different directions, for example, as 1, 0, 0, 0, 1, 0, 0, 0, 1. 1, 1, 0, that is line the diagonal directions for faces. And finally, the diagonals of the cell, that is 1, 1, 1, and all families and directions that close to that. Okay. If you remember, we talked about that, what is the directions? For direction, we use the square bracket, such as 1, 1, 0. Here you see that 1, 1, 0. Or 0, 1, 0 or 0, 0, 1, that for deriving that directions, we need one tail and one head. Tail for this direction is this, and head as same as vector. For finding that, subtract means the x2 minus x1. It is x2 minus x1. y2 minus y1. y2 is the coordinate of the head. y1 is tail. And z2 minus z1. Next step means dividing and normalizing per length of the cell at that direction. For example, A is length of cell in X direction that I can show you. It is A. And length direction in B. Oh. B, and it is C. Okay. That we find that for this case, for example, is -2, half, and 1. The next step means we should multiply all of them in the minimum number to eliminate the fractions, and we reach to integer. For example, for this case, we should multiply in 2. It should be -4, 1, and 2. But we don't show 4 with minus. Instead of minus, we use this bar above that, and we show inside the square bracket without any comma or something. So when we have a square bracket without any comma, means the directions. If you consider that we have the cubic cell, and it is the origins of that. This direction, for example, we don't have any change of x, but y, it is change of y, and we don't have any change of z. So it is 0, 1, 0. Or in next slide, you see that we have different directions. But for the family direction, we use the angle bracket. If you look at here, they are signs of the family directions. So when we use a square brackets like 1, 0, 0, 1, 1, 0, we are talking about the specific crystallographic directions in the unit cell. But when we talk about the angle bracket, such as angle bracket 1, 0, 0 means different directions that belongs to this family. We are referring to the family of directions. That means all the symmetry equivalent directions in the crystal. For this case, 1, 0, 0 includes 1, 0, 0, 0, 1, 0, 0, 0, 1, -1, 0, 0, it is minus 0, minus 1, 0, and 0, 0, minus 1. Why they are important for us, why we should know about directions and the family of that. Many properties of the materials are anisotropic, which means they depend on directions such as mechanical strength, deformations, and even diffusions in metals all vary depending on which crystallography directions we are looking at. Why family directions is important for us. Families of directions make it easier to study crystals because instead of looking at very single directions, we can group them in equivalent sets. In next slide, I show you, for example, different directions that belong to one family direction. In the previous video, I talked about that how we find the family direction. You consider that we have the directions in a square bracket UVW. How we find the family direction? The first step, remove or replace the square bracket to angle bracket or UVW. Then apply the symmetry operations of the crystal. What's the meaning that? Means swap UVW. UVW means start by 1, 0, 0, okay? So 1, 0, 0. First, I write 1, 0, 0 means the family. It includes what? Means includes all directions I want to write that. It should be another direction, 1, 0, 0, comma, swap that means 1 rotate, it should be 0, 1, 0, yeah? And all of them, negative of them belongs to this minus 1, 0, 0, or 0, minus 1, 0. Then rotate, that means 1, come to here, 0, 0, 1, or 0, 0, minus 1. All of them belong to one family. Okay. Here you see different family or different directions. It is directions 1, 0, 0. I show all directions that in this family. For example, it is 1, 0, 0. What is this one? It is minus 1, 0, 0. Same family as the green one, okay? Or instead of 1, 0, 0, we can say it is this one. All of these red one that I'm showing you only belongs to the green one or in one family to green one. I don't want to talk about 1, 1, 0 and 1, 1, 1 in this slide. What is these directions? No change in X, Y change, and Z no change. Okay, opposite directions of this. What is this? It is 0, minus 1, 0. Yeah. Or for example, this. It is 0, 0, 1. What about this one? Opposite direction. 0, 0, minus 1. So all of them belongs to one family. What is that family? 1, 0, 0. Yeah. Okay. If I can change the color here. I show all of 1, 1, 0. What is another directions in that family? It is another at that family. It is another at the family of 1, 1, 0, means the diagonals of the surfaces. Okay. Now let's connect these to linear density. What is linear density, or the abbreviations of LD, is the number of atomic centers lying on along the crystallographic directions or length of that directions. So divided by the length of the line between equivalent lattice points, directions with higher linear density are more close back, and these strongly affect the slip systems in metals, meaning how these locations move. So and how the materials deform. So why LD is important for us for knowing that we have the more packed in which direction. So definitely it has the potential for more deformation or a slip at that direction. Today, we want to derive the linear density in three key directions or family directions of body center cubic crystals, such as 100, 011, or 111. We talk about all of them. I start by directions of 100. I show by the blue color what is 100. 100 means this direction. Yeah. Okay. If you remember, it is BCC. Again, if you have watched the previous video, we told that the more compact directions is along the diagonals of the cell, that is 4R equals root 3A, if you remember that. So how much A? It is 4R per root 3. Okay, we need that. How many atoms we have in these line directions? Look at these directions. Means zoom on that. Half of R here. Half of R here. Means half of atom in one end, half of atom in another end. How many atoms we have? The number of atoms along that direction is 1. So N is 1. What is the length of this line or this direction? According the dimensions of the cell, it is A. At X direction, Y direction, and Z directions, all of them are A. So it is A. So it should be 1 per A. But if we want to substitute A as a function of R, why? Because definitely we have the radius of atoms. So it should be 1, and for BCC, we know that A is 4R per root 3. So it is 1 per 4R root 3. Root 3 go to denominator, should be root 3 per 4R. It is linear density in that direction, root 3 per 4R. Only for that directions, no. For all directions belongs to this family. Now I show you some of these directions. One of these directions is this, belong to this family again. What is this direction? It is 0, 1, 0. Yeah. Or for example, this direction, it is 0, minus 1, 0. Or this direction, it is 0, 0, 1. What is that direction? It is 0, 0, minus 1. All of them belongs to this family. Which family? We can say the family of 1, 0, 0. You see that this is angle bracket. Why? They are belongs to one family, because if you pay attention for all of these directions, linear density is same. Means that they have the same potential about the slip or another things, yeah? Or packing atom at that direction. Another directions that we want to talk about, that it is 1, 1, 0. Means changing of X is 1. I can show you it is 1, 1, 0. Means if you consider the center is this, X, Y, Z. How much difference in X is 1? Yeah, means X increase as 1. How much increase at Y? 1, but no change in Z, so it is 1, 1, 0. Or if you consider that we have this cell, I don't show the atoms for seeing the color. All of them belongs to one family, such as this. It is 1, 1, 0. What is this? It is minus 1, 1, 0. All of them belongs to one family, according to previous slide that I told how we can derive different directions to belong to one family. Why one family? Because linear density for them same. Okay, how many atoms we have? Again, for BCC, we have one atoms at the corner and one at the center of Q. If you look at these directions, half of atom in one end, half of atoms on another end, yeah? How many atoms we have? One atom. The number of atoms along these directions, 1, 1, 0 is one atom. What is the length of that? If you consider this, it is a triangle AA. What is this side of that? It should be a squared plus a squared, 2a squared, and the length of that is root 2a, okay? So 1 atoms per root 2a, and we know that a is 4r per root 3. So this length should be 4r root 2 per root 3 that you see substitute here, and root 3 in the denominator. Add denominator, go to numerator, it should be root 3 per 4r root 2. And it is the linear density along that directions or for all directions belong to this family. Which family we are talking about that? The family of 1, 1, 0. Okay. And the last one, direction 1, 1, 1. 1, 1, 1 means along the diagonals of the cell. Only we have 1, 1, 1? No. If I write the family 1, 1, 1, I can say that it should be 1, 1, 1, or should be minus 1, 1, or minus 1, minus 1, 1, or changing that means different direction. Okay. Look at here. Half of atom here, the full atom here, half atom here. The total number of atoms along that direction is 2 atoms. But what is this length? If you remember from the previous slide, when we talked about the BCC, the diagonals of the cell, it is root 3a. Yeah, or it equals to 4r. If we want to write as the function of r, so instead of this length, only substitute for r, 2 and 4 simplified and should be 1 per 2r. Okay, if I write the linear density in different directions or for different family directions in diagonals of the cell, it is 0.5 divide r. For 1, 0, 0, or if you remember, it means these directions. The directions of the, for example, x, y, z of the cell, it is 0.433 per r, and LD or linear density in 110, if you remember again, it should be align the diagonals of different faces, should be 0.3062. Okay, I put at the tables the family 100 different directions to that family. Family 110, if you remember again, along the face of diagonals of each face, and 111 that you see different directions means along the diagonals of the cell. And here you see the linear density. If you compare the linear density, the more compact is 111, after that 100, and after that, or the minimum linear density along the diagonals of different faces, which explain that the family 111 directions are among the more densely packed and commonly appears as a slip directions. So it has the potential, or most potential, that the slip occur at that directions. Okay. Hope this video help you understand the topic better. As a special thank you, I have created a free study guide that cover what we talk about that today. To get your copy, just find the link in the descriptions of this video. Thank you so much.